In this video, we'll talk about existence and uniqueness, which are two of the main theoretical ideas surrounding differential equations. One of the most important questions to ask about differential equation is the idea of existence and uniqueness. So what do these things mean? Well, the idea of existence is the fact of, is there a solution to this equation? Is there a function y of t that solves my equation that I care about? The sort of pair to this idea of uniqueness, which is really centered around, is this solution unique? That is, are there multiple solutions to this equation, or is there only one solution to this equation? And these may seem like very theoretical ideas. However, when you're trying to do models, it's really important to know these things about the equation you're trying to use, right? In the physical world, right, whatever you're trying to model, it exists, it's happening, and it's doing its thing. And if you set up the same way every time, it will always do the same thing every time, namely that there is a solution, it's going to do its thing. And there's exactly one as well, because it will always do the same thing every time. So in the physical world, these solutions always satisfy these two properties. So the issue then becomes, if I write an equation to model some sort of physical problem, and my modeling equation does not have these properties, I have a problem here. This is not a good situation to be in if the differential equation model I write for a given physical problem does not have uniqueness, then my model is probably not right. So the models we write for physical problems should also have these properties to guarantee you have even a chance of trying to model the real world accurately. Otherwise, we're going to be in trouble real fast. Thankfully, it's not too hard to satisfy these properties when we know things about the differential equation we're trying to solve. So here are the two main theorems that we have for first order equations in terms of existence and uniqueness. So if we have a linear differential equation, that's the first one. This is the linear case. And as long as we know that our functions p and g are continuous, then we are done. We know that when we have existence and uniqueness along that interval, for any initial condition, we are good to go. For nonlinear, it gets a little more complicated. For nonlinear, and you do know that both f and the partial with respect to y are continuous, then on some subinterval, I get a solution. So the main differences here are really the fact that for the first one, I automatically get on the entire interval. Great. For the second one, I don't know if it's going to break at some point, but I, at least for a small time window, get a solution. So just an idea of where these things come from. This one, the linear one, comes from the fact that we have an explicit method for solving these problems. You can always find the integrating factor, multiply it, set things up, divide out. That's our solution. We have an explicit way to solve for these problems, which is why we can always simply guarantee they exist and are unique. For the second one, for the nonlinear one, we don't always have a nice method. This requires a much more complicated proof technique, which we will not get into in this course. It's called Picard iteration. If you want to look into it, you can, but it is not something we're going to be talking about in this course. So that's sort of the idea behind these theorems. They basically tell us that as long as we have it set up in the right way, we're going to have existence and uniqueness of our solutions to these differential equations, which is great to have when we want to use it to model physical problems, because the real world definitely has existence and uniqueness of solutions in this way.